I'll be talking about growth of structure using cross correlation of CMB lensing and cosmic shear. This work is done in collaboration with the people mentioned here under the joint efforts of ACT and DES collaboration. Most of the results are mentioned in this published article. So here is a brief outline of my talk. I will start with an introduction to weak gravitational lensing of CMB and galaxies. Then I will present our cross-correlation measurement between lensing of CMB as measured by Atacama Cosmology Telescope and lensing of galaxies called cosmic shear as measured by dark energy. I will present the inference results about the amplitude of matter fluctuations using this measurement. Then I will go and discuss a bit of astrophysical systematics that one has to take into account while analyzing this kind of measurement. And then so all cosmological radiation is lensed to some degree by the intervening matter distribution between Earth and the source of radiation. Moreover, in a given direction, let's say for any low redshift probe, I'll say galaxies, the matter that is causing the lensing also contributes to the lensing of any other high redshift probe at a higher redshift, say CMB. This leads to correlated distortion between the images of galaxies and CMB in that case, and we can in principle measure this correlation. So here is a demonstration of the effect of CMB lensing. So this image, so the gravitational lensing leads to distortion of the hot and cold spots in the CMB map. These distortions are at the level of arc-minute scale as shown here in this difference image. However, these arc-minute scale fluctuations, they are not randomly distributed, and there is some correlation pattern, and that comes from the lensing potential that is causing the lensing. As you can see, there is this pattern in these fluctuations. Gravitational lensing then can be modeled using this simple expression where we say that at the linear order, what we observe, the lens CMB, is just an unlensed CMB coming from slightly different direction deflected by gradient phi being the lensing potential. So the lensing potential is a line of sight, a weighted integral of the gravitational potential. One can in principle then construct this lensing potential. So this kind of deflection operation causes correlation in the different modes, harmonic modes of the CMB map, and these correlation in different modes is related to the particular mode of the lensing. So to obtain a particular mode, one can go around and get all these pairs which contributes to this mode L, and then have a weighted summation of this. This is generally called the quadratic estimator proposed by Okamoto and Hu. And one can then obtain a quadratic estimate of the lensing potential phi. One generally discusses about the convergence chi, which is a Laplacian of this potential phi, and the convergence then can be thought of as line of sight weighted integration of matter over density delta. Here is a filter version of the map that we use in our analysis. This is obtained from ACT data release 4. This map shows only signal dominated where the white corresponds to more dense regions and the black is under dense regions. Okay. Various surveys have measured such kind of lensing potential over the last 1.5 decades, and the auto power spectrum has a lensing potential map is like a standard data set in most cosmological analysis. Both Planck and ACT and RSPP have measured it up to the sensitivity of 4 sigma. Along with the auto, one can also look into the cross correlation of the lensing potential with other large scale structure tracers. So this map shows you in the background the same map that I showed you earlier. Now overlaid on this are the contours corresponding to the intensity of cosmic infrared background map from Planck. So this gives you a visual inspection of the correlation between CIB emission and the underlying lensing potential. So these dense regions have overlap with high intensity regions, and the under dense region overlap with low density region. In our analysis, we use the cosmic shear to do the cross correlation, so to play the role of cosmic infrared background, for example. Lensing of galaxies leads to correlated distortion in the shape of galaxies, so as shown here by this cartoon. So one can model the observed shape of galaxy as a summation of the intrinsic shape and the contribution from the cosmic shear. For each individual galaxy, the contribution from cosmic shear is quite less. So if one averages over on the 1 Archimedes scale, then the RMS in the intrinsic shape is of the order of 25, whereas the shear is only 1%, which means that per galaxy we have low SNR. Hence, the weak lensing surveys measure shape of many galaxies. The data set that I use, which is DES-3, for example, has around 5.6 galaxies per Archimedes and spans the area of 4,000 square degree. The shear here is like a polarization quantity, spin 2 quantity, Q and U, whose E mode is then related to the convergence. In that sense, shear is also a weighted integral of the matter on the right side. Okay. So why do the cross correlation? Cross correlation provides the advantage that any uncorrelated additive systematic between these two probes it does not affect your cross correlation. Moreover, the cross correlation probe slightly different redshift range than probed by the individual measurement. For example, this plot shows you the redshift and the lensing kernel for CMB, which is at redshift 1100. For CMB, it peaks around redshift 2. For a galaxy distribution, say, which is around redshift 1, the lensing weight is shown here by the curve. However, if one goes look at the cross correlation of these two, the cross correlation is sensitive to this redshift range shown by here, this blue curve, which is slightly different than the probed by the DES provides the galaxy sources distributed in 4 photometric redshifts, and their corresponding length kernel looks like this in reference to the CMB length kernel. So here you can see that the auto spectrum is mostly probing the redshift range up to 1. So the map, the lensing map that I showed overlaps with these parts of the DES measurements, and we calculate the correlation between these two data sets. So these are our data points for the 4 redshift bins along with the best fit after marginalizing over several nuisance parameters. We measure it around SNR of 7.1. So once we have such a measurement, one thing that we can do is compare how this looks in comparison to the prediction based on CMB. We find the amplitude around 0.84, mostly consistent with 1. However, we do need to marginalize several systematic parameters, and their effect is shown here in this plot. The left plot shows you how the observable changes as a function of S8 parameter, which is a combination of sigma 8 and omega, which is the best constraint combination by such observable. However, there can be a multiplicative shear bias in the shear measurement, which doesn't get cancelled. That can also lead to the scaling of up and down of this measurement of the model. Also, the uncertainty in photometric redshift and also lead to scaling observable. Also, the galaxies, even in the absence of lensing, galaxy shapes, even in the absence of lensing, can be correlated. That's generally called intrinsic alignment, because of the gravitational interaction between galaxies. That can also lead to overall scaling. So all these parameters sort of degenerate with the amplitude of the. Okay, here are our constraints after marginalizing over this set of systematic parameters. Our constraints are shown in the blue. Overlaid on those are constraints of 2 different set of measurements, at least at the time of creating this, were the most discordant, most independent to our observable. And as you can see, it's quite weak constraint, so one can always ask why bother about an analysis. So it helps to look at such a plot. What this plot shows you is various measurements of S8 at z is equal to 0 as a function of z effective, where z effective is the redshift of the probe, which is probed by the consists. It is slightly older. There are a few more points about from cosmic shear analysis, which overlap in this region. This is by no means complete. But what you can see is that different probes are sensitive to different redshift range, and they are also sensitive to different length scales. So when we look at different cross correlations, we are trying to fill in the pictures of this kind of picture and give us an idea of the growth of structure as a function of redshift. So next we are currently analyzing ActDR6 lensing map, which overlaps with most of the survey, and we expect to have at least a twofold increase in constraining power based on this. That constraining power is overlaid here in comparison to existing constraints. Okay, in a couple of minutes, I will talk about the systematic. So when one has the frequency map measured at a particular frequency, it can contain various extragalactic foregrounds, for example, the T galaxy or the SDG. All of these things are coming from the regions which are highly dense. So if one is going to construct a lensing map from such a map through a quadratic estimator, all of these foregrounds can pass through it, and these foregrounds and their signatures then can correlate with any other tracer of large scale structure. So these needs to be mitigated. If not mitigated, it can lead to the bias in the cross. So here is a demonstration of such a bias. So just in the present, just with the QE without any bias mitigation, based on simulations, one can see that this is the effect of program, which leads to around 25% bias, for example, in these regions which are typically analyzed. Yeah. After the bias hardening, this can be removed. However, that is dependent on the individual survey sensitivity and needs to be estimated for each combination of probes. Okay. Moreover, there is also the question of intrinsic alignment. If we allow the intrinsic alignment to take broad priors, then we see that there is a significant degradation in the constraint of the asset, which means that we need these kind of things necessitate that we analyze such cross correlation along with the auto power spectra, which allows certain calibration of the intrinsic alignment effect. Yeah. So I will conclude here. Thank you.
Thank you, Shabir.